Hello, welcome back from break. I'm really looking forward to the second half of the class here. So we just finished up on the fundamentals of object-oriented programming. We use C++ as our language of choice, although a lot of the concepts we went over apply to other languages like Java, Python, JavaScript. But we did it kind of the hard way with C++, so you'd be totally ready for other languages. Okay, we're going to continue in C++, but now we're going to start to examine some applications of object-oriented programming to what are known as data structures. And data structures are basically container objects. They're objects that are used to contain sets of other objects in some way. One that we've been sort of using all along is an array, right? So that's sort of a fundamental data structure. But we're going to talk about more data structures that have different properties that are better or worse for certain things. So we'll talk about the trade-offs of them. Okay, and the first one we're going to start with is a linked list. Before I do that, let me motivate it, and I'm actually going to review a bit of what we did in class, but it'll be helpful to go through. So let me start with the following code here. I'm going to define a class just to make this example fully featured, just a very simple class. It's just a pure wrapper around an integer. And what I'll do is I'll make an array of pointers to objects of that class, okay? And I will dynamically allocate an array of pointers to these ints, and I will fill them with wrappers of perfect squares. Okay, so starting at 0, and then 1 squared, 2 squared, 3 squared, 4 squared, etc. And I'll print them out here. So let me compile this program and look at what it does. Okay, so I'll go ahead and compile this, and I run it. And I see some heavy-duty computation that my computer did to compute all these perfect squares. Okay. Now, if you pause and look at this code, there should be a warning bell going off in your head, which I hope you're attuned to by now. And that's the fact that for every new we see in the program, we should have a corresponding delete somewhere. Okay. And it's good practice to, as I said before, delete the things in the reverse order from which they're allocated. Okay. So if I just run this as is, and I use valgrind or some other memory leak tool, I'll see that I'm leaking memory here. Okay. And one thing I could do is say, well, let me delete this array, right? Okay, so I'll do that. And how did I do? So last time I lost 120 bytes. Okay. This time I only lost 40 bytes, but I was trying to lose nothing. Well, of course, the thing I missed is the elements of this array have also been dynamically allocated, right? So I need to delete them. So I did do a good job of deleting the array. So I had a delete statement for that new, but I didn't have any delete statements for these news. And again, you should do these in reverse order from when they're allocated. So let me go ahead and actually remove the objects that I dynamically allocated from memory before I delete the array. Right? So I'll say for int I equals 0, I equals an n, plus, and I'll actually delete the dynamically allocated objects in the array. Okay. So it's important to do this first. So let me go ahead and just make sure that worked. Good. It says all blocks free. One common mistake we should be aware of, though, is actually reversing the order here. So sometimes people will delete the array before they actually delete the dynamically allocated elements it holds. It's a very common mistake. But this is like burning down the map to the treasures that you're trying to find before you go to find the treasures. Okay. So I don't want to burn down the map, because then something that comes in the place of the map is going to be some dangling pointers. I won't be able to actually find the elements that I'm going to try to delete. Okay, so it's important to delete, to keep the map intact, follow the map and delete all the elements before you delete the map. So far, though, that was all just a review of things we've done before. So a review of dynamically allocated arrays and of object references and including memory. But now I want to talk about more of a data structures topic. Okay. So one of the things we're often concerned with in data structures is changing what we're storing. So let's say that we wanted to remove an object from this array, okay? So So let's remove an object at index idx from the array. We can't just do that though, because arrays are one contiguous chunk in memory. If you want to take something out, you have to move everything to the right over. And actually, the array still occupies the same amount of memory. So even if you've made space for one more element, it ends up just being kind of wasted space at the end. So really what you end up doing is, or having to do, is create an entirely new array with one fewer element, and then copy over everything except for the thing you're trying to remove. So that's the game plan. All right, so it's just really 3 steps. So step 1 is create a temporary array, or really just create a new array that's one smaller. Okay, so we got to take out a whole nother chunk of memory that's of the appropriate size. So I'll say int wrapper temp equals new int wrapper n minus 1. Okay, so that was step 1. Step 2 is, well, we're going to copy over everything before the index. So what I'll do is I'll just say for int I equals 0, I is less than index I plus plus. So I'll say this new array temp at index I should hold what the array had before the index. But then the tricky part is actually all the indices after idx get shifted over by 1, right? So I'll say the following. Move over everything after idx to the left by 1 index in the new array. Okay, so what I'll do is I'll start maybe 1 after the index. I'll go to the end of the array, and I'll make sure that actually the new index is 1 minus what the former index was, right? Because I've made space, so everything shifts over to the left. Okay. And that should do it. Now, one thing I got to be careful of is I should free up this array that used to be there, right? So I will say delete x, or sorry, the array error. Okay. So this makes sure that the old array that was too big is now gone. Okay. Let's though. How about we use the same name for this new thing we made? So I'll actually just reassign the pointer that used to point to that old array to this new location. And then of course I got to remember that I'm only then printing out n minus 1 elements and only then removing n elements. Okay. So there's a little mistake I'm making still. So if you see it, I know I'm aware of it, but I want to just see what this does first. Okay. Well, there's an error. That wasn't the mistake I had meant to. I never actually told you what index I was removing. So let's say that I want to get rid of the element at index 3. So that would be the number 9. So 3 squared. Okay. Let's see if we got that. All right, good. There's still a problem, but overall we see that this worked. Okay, so at least it seems you're printing out the correct answer. And so again, notice that I created this new array. I copied everything over except for the thing I was trying to remove. I made sure to delete the old array, which I'm not using anymore, and actually just assigned the new thing that I created to my original array pointer, so I don't have to change much of the code down here. Okay. And actually, maybe to really nail that point home, let me actually, in addition to deleting this old array, I'll actually decrement n, so I really don't have to change any of this code. Okay. Great. So that all seems well and good. Just make sure it still runs. Cool. But if I go back to my trusty old tool Valgrind, I do see that I've actually lost 4 bytes. I didn't do too bad, but there's a very small memory leak here. So pause for a second. Look at what I did here. Try to think, what am I leaking? Okay. So the answer is, and we did talk about this in class with a similar example, I didn't actually delete the dynamically allocated element that I'm now skipping in this new array, right? So I'm skipping that element that holds the number 9, right? And so when I go to print, I don't see the 9. However, that number is still in memory. So in addition to deleting the map and then eventually deleting all the other elements that got reassigned, I need to make sure that before I delete the map, I actually delete the dynamically allocated object at that index. Okay? So I need to actually delete that 9 in this example. So that was one little thing I missed here. So now everything is beautiful. Okay. So we're all set with this program. But that was a bit of a pain that we had this 3-step process. And what's particularly bad about this is that, well, we had to do as much work as there were elements in this array, right? So what if I had an array with 1 billion elements in it, which is conceivable given the amount of RAM we have now, right? If it was an array of ints, well, that would be 4 billion bytes, which is 4 gigabytes. Anyway. So that would take a really long time just to remove one element. And imagine now that you wanted to remove many elements. Well, that's going to be very, very slow. Okay. So an array is not the best data structure if you want something that grows or shrinks. So let's talk about another data structure that is better for this. Okay. And we did this in class, but I'm just going to do a review. So it's something called a linked list. And in C++, it's implemented in something called the STL, the Standard Template Library. And it's called a list, just a list, but it is actually a linked list under the hood. So let me include something called list. I'll say using namespace standard. So that's for STL. That makes it so that I can just immediately use this list class. Okay, so instead of using an array, let me, I'll just call this main2. This is sometimes a little thing I do. That's not actually going to run anymore. Let me make another main that uses a linked list. So I'll go through and I will make the same stuff. But this time I'm not going to use an array. Instead, I'm going to use this linked list. So if I say list, and I'm using something called a template. So I'm saying, okay, this is going to be a list of int wrapper references. Okay, and then what I can say is instead of indexing the array directly, what I can do, I can't actually index the array directly. It's no longer an array. So that's one of the downsides of this data structure. But the upside is I can add things very quickly. I'll draw out why that is in a moment. But just to show you, the command here is array.pushback, and then this new object. And so what that does is that will add something to the end of this linked list. Okay. And so I'll create some similar code to print this out. But it's going to look a little bit different. Actually, there is a class aggregated inside of the linked list called an iterator. And so what I'll do is, so an iterator is actually kind of a pointer to the elements in the list. And we can start the pointer at the beginning of the list and then walk through. So I'll say for this iterator is equal to my list.begin. As long as the iterator has not reached the end, then I will move the iterator forward. Okay. And so what this allows me to do is then, okay, if I then dereference this iterator, it takes me to the element in the list. Okay, so dereferencing, it's like a little arrow that points to different places that I'm in the list. It moves along. And I dereference that arrow to get to the thing that I want to look at. And now I can go ahead and just print like I was before. So unwrap that little int that was in there. And I'll need a similar loop to delete these, right? And actually this was a statically declared list, so the list will be cleaned up on its own. We just need to make sure that we remove the ints that are inside of it. Okay, so let me compile this and make sure that it works. It says fatal error because I called this it, not I. So I wanted to remind myself that it's actually an iterator, not just an integer. So I called it it. That's a pretty conventional thing. Okay, this worked great. So this printed out elements. Whoop-de-doo. Let me just make sure there's no memory leak. Okay, cool. So that's a linked list. Now, let me just draw quickly a picture of this, though, and how it's working, so you can see why it's a little bit different. So a linked list actually consists of a bunch of container objects called nodes that are linked to each other with pointers. Okay. So each container object contains some object that I'm talking about. So here I had, maybe the first one contained 0, right? I'll just put 0. Then the next one contained 1, and then the next one contained 4, right? That was how I had it. I had these squares there. And so the thing about the list is you can't just jump anywhere. It doesn't, unlike an array, it doesn't have what's known as random access. Instead, you always start at the beginning. Okay, you have a reference to something called the head of the list, and you can start there with just the head. Okay, the head of the list. You can start there, and then you can go next. Okay, so if I look in the code here, so begin is the head of the list, and then when I say I++ or the iterator++, this follows the arrow to the next container object. Okay, and so here I am dereferencing the container object to get to this object that's inside of it. Okay, and so I can continue to walk along these arrows, and eventually I'll get to the end and I'll find that there's nothing left, and so the end is sort of one after the last element, and then I find that that's it. Okay, so that's the end of my list. Let me zoom out here a bit. Okay, so that's how a linked list works. And so you're just following these arrows one by one by one. So this is pretty bad if you want to jump immediately to a particular location, but it's very good if you want to add or remove things, as we'll explore in the next few videos. I'll show you how those operations are very efficient. And so it's a great data structure for homework 3 that you've been working on. And I'll have you implement a version of this on the next homework from scratch. Okay. But let's just do a quick exercise on STL's version of this, so just on the regular list that's already given to us, before we proceed. And then we'll make our own version of this.